Hello. Okay. Today, I'll do this contest, DMOPC 2020 in June from DMOJ. And I guess I'll start now. So here's the first prop. Bob and balance. Bob is sitting through another session of physics class, the topic regarding the force of gravity. Blah blah blah. There are 2 N weights and N balance scales. Henry knows that the scale tip with a higher mass. That's pretty dumb. Alright, so basically, all you do is that you want the scales to be as unbalanced as possible. So basically, you can just match if you have the array and pretend it's sorted, you can match the first with the last, the second with the second to last, etc. And then only a few of them in the middle will possibly not be tipped. Hello, Mr. Igor. Are you gonna do that? Alright, so that now I guess I'll just code it. All I have to do is input the numbers, sort them, and put them in pairs. Very, very easy. So I guess you're supposed to output the indices. So then, instead, I'll use pairs and sort the pairs, and then output it, where the first index is the value, and the second is the index. How can it be so insightful? Let's see how that works. Got 1, 4, 2, 3, and 5, 6. That looks good to me. So then now I will submit my solution. What? Oh, that's fine. I guess you're supposed to also output the amount. So I guess first we have to see how many are not equal. And then we print out the indices. Why still don't know what? I guess. Oh. Is that the problem? Maybe that was the problem. Well, no, I should have worked for something. Why did it not work? That's not good. Not sure why it did not work. That is concerning. First line contains n, 2n integers. Why am I not reading? Tip to the right, second was tip. Okay. Third scale means balance. That should be easy. Sorted. Then get the lowest with the highest. Why does it get accepted now? Oh, okay. Why does this only work for? Oh, I'm done. I guess instead, you can just do this greedily. basically, instead of like matching the ends, you just want to find the first one that they're not equal and match them, and keep doing that repeatedly. So then, while and first off, while apply plus and then while j is less than 2 times n, then AFI.f is equal to AFJ dot j plus plus. And now, if j is less than 2 times n, we will match them together. Otherwise, we just do in this case, you're able to match it with one that's not equal, but in this case, you're able to match it with one that is, you're not able to match it with one that's not equal. Why? And you can see that this is what? Alright, you can see that this is now. Why is that? Okay, what am I doing? I'm not off to a good start. So while the ball already picked, we move this forward. The line should be equal to the market is picked. Move J forward. Done. Okay, finally. So this is basically just 2 pointers. This is the first pointer, which always finds the first unpicked value, and then the second pointer finds the first value not equal to it. If there's none that aren't chosen already, then you just find the next value that's not chosen. As you can see, because both iterators only iterate from 0 to 2 to the n, the solution is O, and well then, you also have to sort in the beginning, so it's n log n. Why? What now? I'm getting beat by problem 1. Well, that's unfortunate. Alright, let's think about this more. We'll basically have multiple values that are the same. You need to see how many you can match together that aren't the same. Well, okay. You can always match any that aren't in the same group. The only ones you can't match are when they're the same value as you. Alright, basically all I need to do is keep track of which value appears the most. Whatever value that is, we have to first match with everything else, and then we have to match the rest with it. And then if it's greater than half, we have to match it with itself. Let's just use like a, let's do this in that one. Now what we're going to do instead is do a custom sorting. Where we instead alright, so here's what we're going to do. We're going to sort based on frequency and then do the same thing as the original. this. Now, it should be fine and easy. First, so now, imagine you sort the values by the frequency that they're in the input. So like, imagine you have this case. These are your values here. Then you'd want to sort them to, you'd want the 2's first since they appear the least, then the 1's, then the 3's. So now, if the largest group is less than half, then of course, wait, I'm so dumb. This is the, I'm laughing because I'm stupid. That's fine. Why is this actually hard? Alright. Imagine you have a set where first you have the frequency of every element, and then you store in the set pairs of frequency, and then value. Now, basically, all you have to do is repeatedly get the 2 values in the set, the 2 pairs in the set with the greatest frequency, and subtract 1 from both of them, and then map 2 of them that have that value together. Well, let's show what I mean, I guess. Alright, so what we need is a map. This is vector. We need a set. This is probably way overcomplicated, but at this point, this is the best I can think of, which is pretty sad. Alright, now that we have this, well, size 8. use a priority queue. That would probably be better. So then now we take the two top values of the priority queue, and then we make that a pair. Okay. Ux dot pick, and then x dot pick. Ux dot pick. Do that push. This is probably way overcomplicated, but it's the best I can think of. And then this is pairing up the remaining values that have to be the same. This works. Let's go. I don't think I've ever spent that long on a DMOJ problem one. Let's move on to the next. What in the world is this? Alice is feeling bored in math class. She had said, infinitely large sheet of graph paper. basically this is a construction problem where you want to, all you have to do oh wait, they give you which coordinates are colored, and then you have to output the perimeter. That is a pain. Whatever, maybe we can do that. How would we do that? Somehow we need a way to know which coordinates are like adjacent, which shapes are adjacent. And this is a hard one. Okay, well, think about this. If we have the coordinates of each of the shapes, first off, it's easy to tell if it's a square or an octagon. How? Because you can think about it like a checkerboard. So instead of thinking about it like the diagram on the left, think about this. Think about the squares in the middle. So this would be like the square in the middle of this octagon. If you think about it like this, then it's like a checkerboard. So then it's easy to tell whether each like a shape we're picking is a square and octagon. Based on that, we can like add to a set of points the points we have, and then we can just take the convex hull. No, that doesn't work. Convex hull doesn't account for that. Let me see the next problem. Simplex streets with an initially empty canvas. We have a bunch of VOH FYI. All of that means. Hello, major sample. Alright, let's see. We need to get the points on the outside of the perimeter of the marked points. How do we do that? I'm not too sure. Well, okay. Let's find the leftmost polygon of all of them. That one's of course going to be in it. Now we just try to find repeatedly okay. So we would just find the leftmost polygon, or the leftmost point, the leftmost polygon, and then see where's the next polygon? Does there exist one here? If not, does there exist one here? If not here, etc. I'll think about that later. Some files remain to be drawn out. Empty canvas. An array. Okay. Just half the that's interesting. Alright, so basically for this one, what is this? You're given an array, and you're allowed to put down intervals of different sizes. And you want to see if it's possible that at each position, the number of intervals that are covering that position is equal to the array value. Have I seen this before? No. I've seen something similar, maybe? I'm not sure. The intervals are bounded from L to R. That's kind of weird. Well, think about the leftmost position. We have to have AI intervals touching the leftmost position, right? So then we know that we start AI intervals here. Why would the L to R be at least half of n? I'm not sure. Three concurrent viewers, amazing. Alright, let's see. Alright, so back to what I was saying. We know that there has to be at least AI intervals starting at here, and they have to go to at least L, right? Now, we see for each of these need to also be greater than a of 0, I guess. And then we basically have to repeatedly see if this is like greater than a of 0, we have to start more intervals here. Well, basically, we can start from the beginning and say, when we add an interval here, we say, we'll add some intervals here, and say they have to keep going until L, and then we'll say, we're allowed to lose, like X of the intervals, and then, at R, we'll say we have to have lost X of the intervals. And it's okay that like we don't know exactly which interval stops, because like the next one would be rightward. So like basically you're saying that at this point we're allowed to lose. We can keep track of how many intervals we've started, and say then, and how many intervals we've deleted, and we have to have deleted at least AI, at least like X by R, and we can start deleting X at L. Maybe that, hopefully that maybe somewhat makes sense, but Can we for sure say that we greedily put them down and then extend them as far as possible? Would it ever be better to not extend one and instead start a new one? Why? Why is it greater than n over 2? Well, I don't know. Well, that means we don't have to start deleting intervals from the first one until at least the half point, right? What does that tell us about the answer? I think that's what allows us to greedily put them down. Like, why would we not extend it as far as possible? Is that true? I have no clue. Not too sure. Or are we supposed to extend it as far as possible? Oh yeah, imagine we didn't keep extending it and said we were supposed to start a new one over here. Well then, that would already be to the right of the half point, so you wouldn't be, wait. No, wait, that doesn't. Number 2, P2, that looks very, very battle code is ores. Basically, you're given some of these are highlighted, and then you have to just output all of the things on the perimeter. So then you're just like supposed to start at the leftmost, then look at the nextmost down, and see if that one's highlighted. If not, then you look at the one to the right, see if that's highlighted, and keep doing that. Code Tiger or how far? How far, behind is the video from the chat? I feel like there's too high latency. Oh, that's good. I think there's some setting to be able to change it, but then it decreases my already sad video quality. Let's see. So for this problem is like you have to lay intervals such that for each value in the array, you want there to be AI intervals covering each index. However, the catch is that the interval lengths have to be between L and R, which makes it hard. Not really sure how we're supposed to deal with it. Say they have to go from L to R, and then you would have to start AI intervals at the beginning, so you have to and like keep them going, but then delete AI somewhere between L and R. But I don't think you can just do greedy. L is equal to 1 and R is equal to n. Obviously, you just look at the difference array, and then at each point, like, take the absolute value, sum them. This is pain. Just 1, 4. I think you could solve the problem just greedily if L always equal to 1. I don't know how to deal with that. L not equal to 1. Alright, maybe imagine first you make each interval up to L, and so you keep it as short as possible. You know, but you're trying to minimize the number of brush strokes. How do you know if you made it too long? How would you know? I don't think you can do it greedily. Well, it's not like you can do DP. Why is it important that r minus l plus 1 is greater than or equal to n over 2? It obviously has to do something with the solution. Well, that means you can always make an interval that is like a or minus all this one. Well, that means you can always make an interval that covers around half of the thing, right? Make them cover. This is hard. Oh well. Because I can't solve the third, of course, that means I can probably solve the fourth. Alright, a tree problem. That's one of my things. And cities. And -1 roads. Then there are queries. So that cities can like be turned on or off, basically. Okay, so for this problem, you have a tree. And then some nodes are marked as safe zones. So I'll mark them like this. The colored ones are safe zones. And then you have queries, which are like given 2 nodes on the path between those 2 nodes. How many other nodes are safe zones that are either on the path, that's easy, or are adjacent to the path? That's not quite as easy. But it looks like some sort of reminds me of some HLD problem I saw, heavy light decomposition. So basically, imagine you went for all the... So the most naive way to do the problem is whenever a city is marked as a safe zone. Oh wait, but what if... Oh, okay. Imagine you split it into heavy paths and light paths. So like the thicker paths are the heavy ones. the heavy paths, the nodes on the heavy paths, would keep track of the number of safe nodes that are adjacent to it that aren't on the heavy path. Okay, that makes sense. And then, what else do you need to add? Well, you also need to add. So basically, when you mark a node as safe, if its parent isn't on the same heavy path, then you add one to the node of the heavy path. But if it's the same, then you don't add that node. I think this is the solution. Now, that means the only nodes that you can just take like the sum along a path. That's extremely easy. You can do that with like a binary index tree, not Euler Tor sort. The problem is then, of course, you have the nodes that are like at each point. You have some nodes. When you're at the bottom of a heavy path, now you can just go up the heavy paths and take the sum along the path. But now you have to deal with the nodes that are not on a heavy path. So like some of these nodes could be marked, and you also have to add them. Well, you keep a separate tally of how many total nodes. Wait, what am I doing? The only extra node you have to account for is just if at the bottom of the path. There's like an extra node that's attached to this, right? Oh wait, that's also on the heavy path. Besides that, you never do. I think that's it. That problem doesn't seem very hard. Okay, I'm gonna try coding that, because that looks like the easiest one. Not this. So this is just setting up. A is like is a node marked. D is like wait, all I need is this. A is a node marked. B B will be the bit. So this is a binary index tree, which can basically take a range size. So this is just reading in types. And now what we need to do is to go DMOPC. For heavy light decomposition, it takes 2 DMOPCs. Oh yeah, and I like to zero index all my nodes. Answer queries afterwards. Oh wait, we do need the parent, right? Oh, actually, need to do binary left. Wait, no. We can just use heavy light decomposition. Oh, we also need the sizes. Oh yeah, so basically, if you don't know what heavy light decomposition is, you basically imagine you're at some subtree, right? And there are multiple. You're at a node, and the node has multiple subtrees. Well, you want to connect that node with a subtree that has the largest size, and then the rest of them, that's the heavy path. And then the light paths are the rest of them. What is good about this? Well, as you can see in this problem, it stops you from overcounting nodes that are adjacent but on the same path. And then you can prove that, like, when you go from a node to the root, you go along at most log n light paths. Very simple. Well, it's not very simple to prove, I guess. Well, it's not very hard to prove either. It's kind of like separate. Anyway. Have an hour 48 minutes left, and I've still only done one problem. At least I'll have this one done soon. Maybe I'll do the cancer problem too. Alright, so what do you do for this one? For this, all we're doing is getting the tree sizes. So all you need is one. this is just getting the size of each subtree. And now oh wait. And then what we want to do is make the first value Alright, so this is making sure that the first value in the array is equal to, and the adjacency list, which I'm storing in a vector, is equal to the heavy path. Now what we do is we say, what we want is basically a link to jump from the top of this like heavy path. There are only 3 other nodes you have to check. There can be a node on the heavy path that you haven't added, a node above it on the heavy path you haven't added. Okay, I think I'm doing it all right. Oops. Alright, let's see. Back to what I was coding. Setting aside that. Of course, my DMs have the very, very secretive information. Alright, now I need a code get the heavy path, so then h of I is equal to I is equal to QC0 C I. Alright, h of I is equal to whatever you need. h of I is equal to I is equal to G of C0. You just see it? Then we do. Okay. I'm gonna change my mind about it. So then we can make it like symmetric. This. Your curve. I think that's all I need, right? That has the left and right side of the Euler decomposition. And then it also has the heavy paths. Hopefully that's all I need. Alright, let's see. Wait. How do you know if it's become? Okay, I guess this just swaps, like toggles it. Imagine practicing. What do we do? I used to practice. It used to be easier to practice. Oh well. Let's see. So what do? We add a Alright, so let's see. Now I need to do that function that adds a value to both itself and its parent if it's not on the same path. Alright, then I have to deal at each point if it overcounts when I go over a path. at the top of the path I'll have to deal with. Okay, I think that's all. That's pretty simple. Is that really it? Yes. Oh wait. I need the distance, don't I? I forgot about that. So you need the distance for like when going up. Alright, now you do wall hx. Size is not equal to 1. We do equals Alright, so basically, if I'm starting partway through a heavy path, remember, you're not adding the value to its parent, but that would still be adjacent to it, so you need to add it. Now we deal with this. If x is Alright, so then basically, you can find the least common answer with HLD with this idea. So let's say, let's say there are two nodes that their heavy paths are the same. Then all you have to do is just see. Then it's just the node that's the higher distance up. That's the LCM, because it's a direct ancestor. Otherwise, consider two heavy paths. You see which node's heavy path is the larger distance, and you move that to the top. Hopefully that makes sense. this is... Oh yeah, the beauty about this implementation is that besides this getting you the Euler tour, it also gets you, because you always DFS down the heavy node first, from the Euler index of this node to this node is continuous, which is why you're allowed to just query along a range. So then what I'm doing is just finding the value along the heavy path, I guess. And then you also have to subtract. You also have to subtract a of h of x. Why? Because we're saying this is not the top heavy path, right? That means a of x, if it's turned on, will be added here, and it will also be added into this heavy path. And we don't want to double count. Alright, this should be correct. Now, all we have is where now we just have to add the last case. Which is skills. And then you have to see if h of y is equal to y, this is just adding the node above the LCA, because that could be if wait, no, we need to add it no matter what. Yeah. Alright, so like the node above the LCA would be counted. So we need to add it. Y. Oh, why is it 2? What did I mess up? Let's look at the tree. Alright, which node is turned on? We say the value 4 is turned on. And now we're asking the query from 2 to 3. Well, we can see. Oh wait, I'm double. You only add this if it is Hold on. No, I'm doing something wrong. X0, that's the heavy path. What am I doing? This will be the heavy path. Using the binary index screen, correct? No. One now. Well, now how's that? This is tiring. But I should be almost done. Why is this heavy? Oh. I see. So we need to only add that child. Making sure that one is not in the subtree of the other, because otherwise they'll be added. Okay, now this should get full points. Let's go. Full points. Why? Why? Well, this is disappointing. What am I doing wrong? Is my bounds right? Yeah. I don't know. I think I did everything right. Did I misunderstand the problem? This should be elements. Maybe that's it. And this could cause. Alright, come on, please wait. Hola. I'm doing a DMOJ. Basically, the problem that I'm doing right now is, why is this here? Is you're given a tree, and you can turn the nodes on and off, which I have marked as like marking them with white on this diagram. And basically, you want to see is you're given queries where the queries are between two nodes, and you want to know how many nodes are turned on that are either on the path or that are adjacent to the path. So like they're not on the path, but they're one away from the path. And basically I'm doing some heavy light decomposition, which I just finished coding, but it's not working. So now I'm trying to fix it. Not too sure what I'm doing wrong. So right here, this is just coding a heavy light decomposition. Alright, let's see. Let me go over what I did and see if I can figure out what I did wrong. Alright, so the cases are a heavy path is the path from a node to its largest subtree. Now, let's draw the heavy light path diagram. So in this diagram, the heavy paths would look like, would be a heavy path along here, and along here, and then along here. These would be the heavy paths. Now, we're only adding, so like the problem with just like adding a value to its parent is that we'd overcount when like both two nodes are on the path. So like if we just added a value to its parent, that would overcount. But with the heavy light decomposition, we can stop that overcounting, since we'll only add the value to its parent if its parent is up a light path. Now, what am I doing wrong? When the node is, let's see. Alright, so first up, at the bottom, so we're finding queries between two nodes. For the bottom node, because we're not adding a value to its parent if it's on the same heavy path, we'll need to add the value that's under the starting node. This is what we're doing here. that would be right here. That is what we're doing. We're making sure that if one node is inside of the subtree of another, that you're not adding that. D of x is greater than dy. Only if that node is outside the subtree do we add it. Okay. That should be right. Now, while h of x is not equal to h of y, we're using the Fenwick tree to query along a path. That should be getting all the nodes that are turned on the path, and all ones that are children on the light paths. Now we'll have to go up the light path. Go up the light path. If this node is turned on, it will also be added to here. So we need to, and this will be added when we go along this path. So we need to subtract it out. That's what we're doing here. Go up. Okay. Wait. Hold on. Oh, so be cute. Let's say the top of the path is here, but x is coming from here. Then you'd also have to add that heavy path value. Wait, how many more times will something like that happen? Wait, hold on. I think I see it. Okay, look. Imagine we started here, went up the light path. We forgot to add this heavy path. Okay, I think I know what to do. So basically, you can get rid of all of this, because it's useless. There we go. That should be it. Now, oh, well that didn't work. What'd I do wrong? I'm not sure. Alright, so what do? We fix, well we try to fix how it's dealing with the extra. Two, three. One, two. 1 and 2? Okay. Now. Wait. Oh no, it doesn't even matter. No matter what, I should be adding this. Yes. I think this is right. Alright, I think this will work. Let's see. Oh shoot. So close. Runtime. How did I get at this? What is this? Yeah. Apparently my headphones are falling apart. That's not too good. Let's see. What can I do now? Obviously, I'm on the right track now. Let's just do so close. What now? All right. Figure this out. What are we missing now? I'm not sure. Must be something small. Wait, what about a size 2? Okay, wait, what about this? Not PXC. Alright, I think that was the problem. Just missed those stupid small cases. Yes. Oh. Let's go. Finally. That was a nice problem, I guess. I figured it out pretty quick. It was still fun to code. This is done. $53 left. Alright. Test cases. Alright, back to this. We now don't need this stuff. So basically, for this problem, you have a tree. Back to what I was saying. So you have a tree. And so then every node has a cost. Let's call that B. Okay. But every edge has a profit, has like a reward, AI. Now, to be able to get the profit AI, you need to select both nodes that the edge is adjacent to. However, when you select a node, then it subtracts that profit, subtracts that cost B of I. Interesting. Well, this doesn't look incredibly hard. Why can't we just do... Why can't we just do like a DP of a... Doesn't this work? Am I misunderstanding something? Oh! Wait. I'm dumb. This isn't a tree. This is just a general graph. That's pretty hard. Alright. So scratch what I said about the tree. This is just a general graph. I see. Alright, so we can't do anything that's like DP. That makes this a lot harder. What do we realize? Well, we only have n nodes and m edges. And they're 500. That's like a O(n) cubed. What could this be? We know that UI and VI. Could we do... I don't know. For some reason, this feels so much like some sort of Gaussian elimination problem. But like, you can't really set up a linear equation. I guess it also kind of looks like minimum spanning tree. But like, what would that look like? Where each edge has like a weight. I don't think that's right. Alright. It's definitely pretty hard. All based on... Do we want to think about it as picking nodes or picking edges? Oh no, this feels like minimum span tree. So like if you create each node as like AI minus BI minus BJ, but like when you take it, then now all these edges no longer have to use BI. Well, okay, let's think about this. It's connected components. Alright, basically we have connected components, right? Let's imagine we pick some. Well, I guess basically in this case we'd only pick this. If we had this, said it was a single connected component, then we know the exact cost on it, because it's just the sum of the edges between nodes in the same component minus the nodes. So then, I guess the question is, then, what nodes do we split so that they're in separate connected components? It's like cutting the graph. Cutting. Right? Because that means basically every node next to it then was not selected. Interesting. If every node is not selected, well, I guess that kind of looks like flow then, right? Like a minimum cut graph. What exactly? When you cut a node, it will also take out all the edges around it that haven't been cut yet. I don't think we can just greedily take them though. Greedily take the largest cost, cut it, because that could also take the good edges too. Or we just say the node. Well, that's like the same as the GoPro. We need something more. We talked about partitioning the nodes, the cut, just like minimum cut graph. Wait. Flow. I know what this looks like. There's that stupid flow problem. That's like you have a... Okay, I know how to solve this. What's that? I'm just gonna do some copy pasting because I'm lazy and useless. Yeah. Where's the one that I use all the time? Is it it? No, that's not it. What's this? Okay, I can just basically copy paste this, right? Probably. I'm not sure I can even code flow anymore, so copy paste it is. Wait, how does this work? Do I even remember? I'm pretty washed, I guess. I haven't done anything with flow for a long time. Alright, let's see. Wikipedia flow. Max. Wait, it should be the... Is it this or that? Okay, I think it's under this one. This one, project selection. Duh, it's exactly this. Such a shame. Alright. So, the cost to here. This is the cost. That's a pretty cool idea. So basically, this uses the max flow min cut duality. So imagine you create a graph where, so each of these things, the Q's give you profit. However, the P's, to use a thing Q, you need to first buy P1 and P2. So then, imagine you create a graph like this. You want, so now, you want the minimum value of edges you have to cut so that S is disconnected from T. And that will give you, and then the remaining edges will give you the maximum profit. You may wonder, why does that work? Well, this is because, think about it. So if you cut an edge over here from like S to P, that's the same as saying, alright, we're not gonna buy this in the beginning at all. However, if you cut an edge over here that says, we're not gonna use this at all. Right? Right. Wait, what? Do I understand this right? Yeah, go for it. Hold on. What? Oh yeah, if you cut this, that's like you're subtracting. That's like you're buying this. Otherwise, if you cut this, that's like you're not buying this. Alright, I think it makes sense, more or less. So back to this. Should be 1,000. Alright, so basically right here, this is just a flow template for like the pushing relabel algorithm. Easy. All we have to change is which edges we're using. Simple enough. Alright, so what's the input? N and M. Okay, now what we do is we read in the value for the edge, and then we do edge, M, Y, this should all be like N, S, M. Okay. What is K? I don't even know what K is. I don't think it matters. K. That must have been problem specific. We need to start this. Do I have to make this all long? I think I do. That is a pain. Long.
I can see it right in front of me.
Are you sure? saying this right. Hopefully. Bop, beep, bop. Now I just have to make sure I modify this all right. Did I do it right? No, not even close. What? How did I get that wrong? That's a pretty large amount of wrongness. Oops. Well, yeah, that does seem like a problem, I guess. But did not fix it very much. Alright, let's get the original one.
And I can't think of any other global movement that promotes peace, ideals, values on this big,
Oh,
beautiful planet.
wait. You only
Celebrate
had
the
here.
centuries of the dead.
Shoot. That was close, I guess. I don't need this. Alright, what am I doing? Did I modify something wrong? Wait, what? How do you... Let's look at the read it. Look at read it. should be adding this. Idiot. There we go. This should work. I believe I can fly. Oops. Oh, let's go. 0.03 seconds. Nice. Well, I definitely have a pretty weird solve graph, I guess. I guess, based on this, I should try the last one. And you, it's the Demon King, some other world. I guess that was a standard problem, I guess. I just haven't done flow in a long time. Mao is the Demon King of some other world, consisting of a single peaceful and quiet kingdom and villages. It hurts to wear headphones for a long time. Alright, anyway, back to and villages, 2D points, bored out of his mind, relatable. Now decided to divide the villages into two conflicting nations and witness the ensuing vandal. Minimum distance. Interesting. I'll check my DMs after. Well, this is interesting, I guess. It's kind of weird, bro. It looks very hard. I have no clue how to solve this. No. reminds me kind of like the ham Swiss cheese theorem or whatever. Well, it's not that. I don't really know. I'll go back to problem 3. If I could solve 4 and 5, why can't I solve 3? I'm just too lazy to code 2. I could do that. I'm taking these off. This hurts. Oh, that hurt my head. Do I still have volume? Hello? Hello? It seems so. Oh, that hurt my head. Oh. Senpai and art. Why can I not solve senpai and art? Alright. Oh, yeah, wearing headphones for a long time, not a good idea. I should have just had them off from the beginning. One layer of paint. Any summary? Man, this problem's hard. Why is this way harder than this one? Well, I'm not too sure. Still, it's quite a hard problem, but it must not be hard. I'm just missing a very easy idea. What about this? Think about all the values in the array that are minimum. We have to have lines going through them.
Larry, I know what I'm going to do tomorrow, and the next day, and next year, and the year after that. I'm shaking the dust of this crummy little town off my feet, and I'm going to see the world.
14 minutes left. Can I solve this in 1 minute? Probably not. I haven't solved it. There you go.
move, all right?
I'll take it.
You have to start AI here. You have to start AI here. Alright, let's imagine solving this with a really bad complexity. No, that won't work. Alright, imagine this. When you put down a line, everything from the start to L is just subtracted, right? Of course. You have to subtract one from those. Now, from L to R, you're allowed to put lines of size. You're allowed to put up to like AI lines from size 0 to, right? Sure. And they have to start from the beginning. They can end. Okay. Why is L not greater than over 2? Wait. Alright, imagine all the AI less than L and R. Well, they are basically, no matter what, if you start from the beginning, you have a certain amount you have to put down, right? They have to be increasing because you can only add more lines. However, once you get to L, things start to change. Now, you have some intervals you're allowed to put down. Whenever, and stop before R. Right? Sure. So first off, alright, let's say after L, you need an interval. You have two choices. You can use one of these intervals, or you can use this one. Oh, I see. So basically, you want to maximize the number of... Wait, what? No. Yeah. Remember, L minus R is greater than N over 2. So remember, what did we say? These ones strictly increase, or no, non-decrease. Now, some places we're allowed. Why does it matter that R minus L's greater than N over 2? I'm not sure. But I think Alright, when do we want to choose to add a new long interval or extend a short interval? Well, we know we want to extend a long interval. When what? Well, if this can extend farther than the length of R minus L, if L, oh, is this where it comes in? Is this ever true? Alright, R minus L is greater than N over 2. That means L is at most N over 2. Right? That means we'll never want to add a long interval when we can instead add a short interval. Because a short interval can be longer than the long interval at the same point. Oh wait. Well, that's not true. But what about when R minus L goes past? What about when L? Not only must all be greater than r minus. Well, that's not the only case. L can be less than r. R must be greater than r minus L. Well, that's always true. No, it isn't. What do you have? No, it isn't. Yeah, it is. R. Well, that, okay. R is R squared. Why? Well, no, you have to extend it longer now. Maybe I can go longer than R minus L. Oh, 2 minutes left. Whatever. Oh no, I think the greedy would have just worked, but I don't know how to prove it. The greedy is just, so like you add the intervals whenever you have to, and then you think about the small intervals. You just extend them as far as possible. I think that would have worked, but I have no clue how to prove it. How disappointing was that? Whoops. If you could reach farther than R minus L. Okay, L is less than or equal to R minus L. That means if it can reach farther than R minus L. Oh, that's how you prove it. Okay, okay. Basically, you look. Can you add something longer than R minus L? If so, wait, wow. Never mind. Add longer than R minus L. If you extend it out too far. And then alright, hold on. So it looks like the contest finished. Let me see. Did I actually? Okay. So what were the rankings like? Remember, I got 4 and 5. Most people got 1, 2. And some got partial something. Okay, it looks like 3 was definitely harder than 4. not too many people got 5, even though I thought it wasn't that hard. And then, yeah, 2 wasn't that hard. I didn't think it was that hard. It didn't seem very interesting to code. And I thought it would take a little bit of time. Wait, what? How'd they do it in 9 minutes? Oh no, there must have been an easy way to code it. I didn't realize. Well, yeah, look at these people. They're coming like an hour on this. Oh well. Well, I guess that's all. That's all for this contest at DMOJ, DMOPC 20 June. You should try the problems yourself. I think they also have editorials, so you can look at those. Oh wait, I guess they bumped up the points because it was so hard. Yeah, that's a hard problem. Well, I'll think about it. You should think about it too. And, goodbye, I guess. Adios. Hasta luego.